Hey guys, welcome back to Business Statistics. This is Module 7.1 and 7.2, Interval Estimate and Sample Size Requirements of the Population Mean with a Known Population Standard Deviation. Okay, so the important things in that title, I know that is a lot. That's a lot of words. So two concepts that we're going to be looking at is interval estimate, which is otherwise known as a confidence interval, and then calculating a sample size. Okay, that's what we're going to cover in this section. And then like the stipulation is that we just know a population standard deviation, okay, or that we're given one. So that's that. So that's what's going to differentiate this section from the next section is that this, we are given a population standard deviation. The next one, the next video, 7.3, we're not given one, okay? So that's that. Let's get into the definitions. Definition of a interval estimator, also called a confidence interval. You'll hear me refer to it as a confidence interval always. The only reason I give interval estimator on there is when you're doing your pre-work or when you're doing your quiz, the book, or if you want to call it that, the learning software might refer to it as an interval estimator. Okay, but it is also called, and more formally and more generally called, a confidence interval. Okay. That's a range of values derived from sample data that has a certain probability of containing the population parameter. Okay, so we establish a certain probability and we want to make a range where we think that the population parameter resides with a certain level of confidence. Okay, so confidence level interval tells us the likelihood that a given interval will contain the target parameter we are trying to estimate. Okay, and so now here are the formulas for a couple of the concepts. Okay, formula for the confidence interval is going to be x bar, which is our sample mean, plus or minus z alpha half. Okay, z alpha half is just a z value times sigma divided by the square root of n. Okay, and we formally define our margin of error as that plus or minus piece, that z alpha half divided by z alpha half times sigma divided by the square root of n. Don't let this formula scare you. I know that it's crazy. I know that it looks nuts, but it's not. Okay. I know that there's a lot of symbols going on there, but we are going to get into all of them. So don't look at this and be like, "Oh, I can't do this. This is nuts. It's crazy." Don't do that. All right. We'll get there, and I promise you. Well, I hope. I don't want to promise, but I hope that this concept will make sense. I'm going to do my best to make so that it does. Okay, so example 3, a computer company makes its own computers and delivers them directly to customers. The manager of the company knows from experience that the demand during lead time is normally distributed with a standard deviation of 75. He observes 25 lead times and records the demand during each period. With a sample mean of 370.16, construct the 95% confidence interval estimate of the mean during lead time. Interpret the confidence interval. Okay, so first, let's write down what we have. So before we even get into the problem, before we even kind of worry about whether we know what's going on with this, let's write down what we have. Okay, we have a standard deviation of 75, so a sigma of 75. He observes 25 lead times. Okay, so there's 25 observations, so the sample size is n equal 25. Okay, and then we have a sample mean, so an x bar, not a mu, an x bar of 370.16. Okay, let me adjust this tablet as well. Okay, so, and then it's asking us for a 95% confidence interval. So I'm just going to put CI for confidence interval. So now I'm going to describe this concept of alpha. Okay, so alpha refers to our type 1 error, okay, or essentially our probability of being wrong. Okay, our probability of assuming something and assuming it in error. Okay, and so our probability of assuming something in error, in this regard, our alpha error, okay, is just going to be alpha equal to 0.05. Where do we get 0.05 from? Well, it's really easy to determine. Okay, when we have a confidence interval, it's just going to be what's left over. So if we want to have 95% confidence in something, what's left over from that to get to 1? Well, there's still 5% left. So that's going to be our alpha. So it's just 1 minus the confidence interval. Okay, so that's our alpha. That's going to be important because that's going to help us define or to find what z-value we're going to use. So if we look at our formula for confidence interval, the formula that we're going to be using is the confidence interval formula. We have an x bar plus or minus a z alpha half, so z sub alpha half, times sigma over the square root of n. Okay, so we have n, right? N is 25, so we have that. We have sigma, that's given to us in the problem, that's 75. We have x bar, that's given to us in the problem, that's 370.16. And now, the last thing that we have to find out is z alpha half. Okay, so we determine, because we're looking for a 95% confidence interval, that our alpha is 0.05. Our alpha is just 1 minus the size of the confidence interval. Okay, so it's just the area outside of our confidence interval. Okay, so now the z-value that we're going to find is 1 for alpha half. Okay, so not for alpha half, and it'll make more sense. I'll kind of draw a picture and show you why that is, but it'll make more sense in a second. So we're looking for z of alpha half, so z of 0.025, not z equals 0.025, z of 0.025, right? So this is where we are then to look inside of the table and look for 0.025, okay, in order to find a z-value. Okay, and I'll just say right off the bat, we don't have to worry about signage here, like whether it's positive or negative, because within the confines of the problem, we are already on a plus or minus basis. So a negative is going to end up operating as a positive is going to operate as a negative, so it just does not matter. Okay, and we'll see why here in a second. So if we want to look on the negative side of the curve, we're going to look inside of the table for 0.025, not as a z-value. Okay, we're looking for that as a probability. So let's start up here in the top corner, and we just walk down the 0 column until we get to something that looks like 0.025. Not this, there's too many decimals there, too many zeros. 0.0179, 0.0228, we're getting close, 0.0287. Okay, it looks like we already passed it. So now we're at like z is negative 1.9, so we're gonna walk this way. Hopefully you guys can see my cursor and I'm not just sounding like a crazy person. And we walk all the way down here and we are at 0.025 or something very close to it, right? This is in fact 0.025, but you'll see when we're doing other z alpha halves that we won't get exactly that, and we'll have to estimate a little bit. All right, so we found it here. So 0.025, and this corresponds to what z-value? We look over here, negative 1.96. So 1.96 is what we can use. Okay, so we go back here and 1.96. Okay, so think about this in terms of we're taking an x bar, so an x bar kind of right here, and we're varying it a certain number of standard deviations. Okay, and so this is why, so we want to vary it to here and vary it to here. So in this area, we're going to have our 95% confidence. And on these areas, we're going to have the rest of our probability. So we're going to have alpha. So we have 0.025 over here and 0.025 over here. And this is why we're looking for z alpha half, because we want the z to vary this way and the z to vary this way. So the error that we're going to have is going to be split between two tails. So that's why we divide out that 2, because we want to have our 0.025 on one side and 0.025 on the other side. Conversely, you could have found our z alpha half in the table on the positive side of the table. We just would be looking for 0.975 on the positive side of the table, because that's what's going to leave 0.025 on the right hand side of it, right? So if we look back at this little diagram that I drew, If we had 0.025 down here on this right-hand tail, it would leave 0.975 of the area before it. Okay, so if we're looking here, we would just then be looking for 0.975 in the table. So we would walk up here, 0.9767, walk over here, boom, 0.975. What z-value is that? 1.96. 1.96. So it's going to give you the same z-value, and that makes sense, okay? I know that this concept is not the easiest to understand, so if you guys have questions on this, please email me. Please, hit me up in the discussion forum, and I'll be happy to answer any questions you have on that, because I know that it's not something that just comes naturally. All right, so for some people it does, that's for sure, but for some people it doesn't. So our z alpha half is negative 1.96. So what ends up happening is we just plug in the numbers. So our x bar is 370.16 plus or minus 1.96 times 75 over the square root of 25. So on the negative side, so when we do this as a negative, we get 340.76. So this is just me not worrying about the plus symbol and just minusing off that piece. And then on the positive side, we get 399.56. Okay. And then depending on the units, you might turn it into like whole numbers. You might have to round in some capacity. Okay. All right. So now the last part of the question says interpret the confidence interval. So just what is the meaning of this confidence interval? We just came up with this interval. All right. What does it mean? Okay. So this is a very, very important piece. So listen closely when I say this. So this interval, 340.76 to 399.56, okay, or something very close to that, is an interval for which we have 95% confidence that our mu resides in. Okay, right. So everything that we've been doing up to this point, like we've had sample statistics, we've had an X bar, right? But we're saying that we're trying to like kind of triangulate. We're trying to find mu, right? So an estimate of mu would just be X bar, right? Like if we wanted to estimate, what the population mean is, we just take a sample mean and we say, okay, well that's a decent estimate. Well, how sure can we be? Well, we can't be sure at all on a sample mean. But what we can do is take a confidence interval. When we take the confidence interval, we establish an interval where we have 95 or whatever it is, but in this case, 95% confidence. So we're 95% sure that mu is between 340.76 and 399.56. So that's where we think the actual population mean is, with 95% confidence. And we know that 5% of the time we're going to be wrong. Okay, but 95% of the time we're going to be correct. So it's kind of a big interval, right? So we don't know with a lot of confidence what the actual number is, but we know with 95% confidence that it's in this interval. All right. And then more conceptually, like so just know that, but more conceptually, like think about the things that would change this interval, right? Think about the things that would make this interval like tighter. Like if we wanted more precision, if we wanted more accuracy, right? Well, what could do that is we take a larger sample size. Rather than 25, like bulk this thing up to 1 million, right? I don't know what number makes sense in terms of this problem, but bulk it up a bunch, okay? And then notice what that does to the formula, the x bar plus or minus z alpha half times sigma over square root of n. The larger n gets, okay, the larger that number is on the bottom of the fraction, and then thus the smaller that margin of error is, that the plus or minus. Thus the smaller that is, meaning it's going to vary from x bar with a much smaller number, which means it's going to tighten up that confidence interval. It's gonna shrink the confidence interval. Okay, so that's the concept there. this is the type of video where you might need to rewatch it. You know, maybe I'm talking too fast or something. But yeah, go back through that if you need to. And that's that. All right. So formula for counting, for determining sample size. This is a formula that's just derived from the confidence interval formula, where we just kind of isolate. We isolate n. And so that's n equal to, in parentheses, z alpha half times sigma divided by the margin of error squared, the whole thing squared. Okay, and then the rounding rule for this is always round up. Okay, and that'll make sense as we do this problem, I think, why you would always round up. Okay. The operations manager of a large production plant would like to estimate the average time workers take to assemble a new electronic component. After observing a number of workers assembling similar devices, he determines that the standard deviation is 6 minutes. How large of a sample of workers should he take to be able to estimate the mean assembly time to within 20 seconds at a 99% confidence? All right, so a lot going on in this problem. First thing I want to point out, which is not generally the first thing that I would do in solving these problems, just note, and this problem's kind of annoying, but note that one of these things is in minutes and one is in seconds. Okay, so that's kind of annoying. So just make sure you're aware of that, and then you have to change the units accordingly. Okay, so we'll just solve it in terms of minutes, and that's that. Okay, so what do we know? Well, we are given a sigma, a standard deviation, population standard deviation of 6. How large of a sample of workers should he take to be able to estimate the mean assembly time within 20 seconds? So within, that's our margin of error. So with a margin of error of 20 seconds. So our margin of error in terms of minutes is going to be equal to 1/3 of a minute. Okay? At a level of 99% confidence. So 99%. So then this implies that we have an alpha equal to 0.01. All right? And then furthermore, an alpha half equal to 0.005. Okay? So let's look at our formula. We have n equal z alpha half times sigma over e squared. Okay, so what do we have? We have our sigma, it's given to us in the problem. We have our e, our margin of error, 1 divided by 3, or 1/3. And z alpha half we need to find. Okay, so now we're looking for z of 0.005. Oh, did I not write that? Z alpha half. Boom. Okay, so let's go to our table. And these numbers you're not always going to have to look up. The alphas that we use are very standard. We're always going to be using a 0.05, a 0.01, a 0.10. I generally like to just tend toward 0.05, but every now and then I'll use 0.01 as well. So inside our table, let's look on the negative side because it's always easier, because it's always the alpha half that we're looking for. We're looking for 0.005. So we go down here and we've gotten past now 0.005. We walk over. Okay, we get to 0.0049, 0.0051. Okay, so it's kind of in between there. All right, so I'm generally going to go with the larger z value. So not the larger probability, but the larger z value. The reason that you do that is because it's including more probability into the confidence interval and excluding less in the alpha, right? So right here is our number. So this is our 0.005 essentially, and this corresponds to a 2.58. So 2.58 is our z alpha half in this regard. 2.58. So now let's plug in our formula. So n is equal to z alpha half, so 2.58 times sigma of 6 divided by 1/3 squared. So it's just going to be 2.58 times 18 squared. And that is equal to 2156.67. And because we're talking about a sample size, we're always going to round up, because we want to know what is the minimum sample size for which we can have 99% confidence here, right? So whether we were at 2156.23, we would then round up because we want to have that next unit, right? Because n can't be a continuous number. N needs to be a discrete number. So 2157. That's that. Guys, let me know if you have questions on this concept. We're going to be doing this concept of sample size calculation and confidence interval calculation a bunch. But yeah, until next time, thanks so much.